So today we are going to discuss the two-phase simplex method, which is required for certain particular cases of linear programming. This is lecture 32 and I am Dr. Ranjan Ganguly. Now let us go through the standard LP problem just to refresh the memory. So essentially we want to minimize a linear objective function f is C transpose X, where C are the constants or coefficients and X is the design variable vector. And this is subject to a linear system Ax equal to B, where all the bi coefficients are greater than equal to 0 and the xj are also greater than equal to 0. There are m of these equations, so there are m number of b coefficients, and the design variable vector xj has size n. Now, if the problem has just less than equal to type of constraints with non-negative right-hand side parameters, then if you simply add slack variables to the problem, you get the canonical form. So in these type of situations, the basic solution that you need to start the simplex method is obtained straight away by setting all the starting design variables to 0. Now, if you have followed my book or some other books on the topic, you will realize that if you have less than equal to type constraints, the canonical form can be obtained straight away and you can get a starting initial basic solution and then you can solve the problem. But many realistic situations have LP problems which have greater than or equal to constraints. And in these particular situations, the initial basic solution is not there for you. So there is one more step which you need to do, and that is known as the two-phase simplex method. Now, to obtain this starting basic solution, we add new non-negative variables to the greater than type of constraints or to the equality constraints. So we peruse the constraint equations and see whichever are greater than or equal to in sign, and we add these new non-negative variables to these particular equations or inequalities. Now these are known as artificial variables, which we shall call AV, and these are different from slack or surplus variables. These variables are essentially numerical constructs which permit us to obtain a basic feasible solution to start the simplex method. So once we start the simplex method, then we can go back to the previous type of problem which we had. So when we add these AVs to the problem, you get a starting basic feasible solution by treating these variables as basic. And this leads to the two-phase simplex method for LP, which is needed whenever you have greater than equal to or equal to constraints. So essentially here in the phase 1 of the simplex method, you create a new cost function W, which is the artificial cost function, and here you use the m variables which are also new variables which have been created for the problem. So we will denote these as xn plus 1, n plus 2 to n plus m. Recall that there were xn design variables in the starting problem. So m number of new design variables have come in because of the presence of these AVs. And in summation notation, we can write it as I is 1 to m xn plus I. Now the constraints remain the same, except you will notice that there are these xn plus 1, n plus 2 to n plus m variables which have been put in here. And so this is presuming, of course, a complete set of these variables here. And so this is the maximum you can obtain. Now, of course, all these variables must be greater than equal to 0 all the way from I to n plus m. And the values ranging from n plus 1 to n plus m are the AVs which are given by this particular last term set here, xn plus 1, n plus 2 to n plus m. So these are the new variables which have been created because of this two-phase simplex method, and now we are going to solve this problem. And essentially we want to minimize this function w here. Keep in mind that all the x's are greater than equal to 0, so the minimum value of this function w should be 0. Now if we write the summation in the constraints in a summation form, we get something like this. So again, recall this is the constraint aijxj sigma equals bi, and these are the AVs which we have put into the problem, the xn plus I. And therefore I can write these AVs out in terms of the older design variables xj. Now take this and substitute it into the new cost function w, the artificial cost function. And here this cost function is I is 1 to m xn plus I, and so I substitute this xn plus I here. I get this equation here. The first term is a constant, so I can write it as f0, and the second term we can write like this, provided that we define that these reduced cost coefficients Cj dash are negative I is 1 to m aij, which we have extracted out of this particular equation here. So again, rewriting this equation here for completeness, we now have this new cost function w is f0 plus this sigma term. Now of course f0 is a constant term, so it is not going to play a role in the minimization. Therefore the cost function which we have now w can be written as ctx, which is c transpose into x, which is just a way of writing this summation j is 1 to n. Now f0 is a constant, and therefore the standard simplex method can now be used to minimize this cost function w, and the starting cost function which we have, which was the f, is treated as a constraint here. So let us look at the phase 1 of this simplex method now. So you start the problem by introducing slack and surplus variables in the constraints and express them in standard form. So that's the usual process. At this point you check that all the bi should be greater than 0. If the jth design variable yj is unrestricted in sign, you substitute this as yj plus minus yj minus, where both these are positive. So this is our usual process of converting the LP into the standard form. Now define AVs for all the greater than or equal to type of constraints, and these will give you a canonical form for phase 1. Now define the cost function of the AVs, which is known as W, and express this new cost function W in terms of only the non-basic variables. Create a simplex tableau for the problem. The cost function W is written in the last row and the starting cost function in the second last row of this tableau. You scan the last row of the tableau, which corresponds to the new cost function W, and note the most negative coefficient. Let the index be r. This implies that xr should become a basic variable. Calculate the ratios of the right-hand side parameters with the positive coefficients in the column and select a row S. This implies that S should become non-basic. If there is no pivot point here, the problem is essentially unbounded, and so you have to look at your problem again. Now if you have a proper pivot point, perform the pivot step on the rows of the tableau with ASR as the pivot and the Sth row as the pivot row, and also check for negative entries in the last row. Now if all the entries in the last row are non-negative and W is 0, then phase 1 of the simplex algorithm is complete, and essentially you have successfully minimized the function w. And therefore a starting basic feasible solution has been obtained for the problem. Now, if all these values in the last row are non-negative and w is not 0, that can happen in some cases, then the problem is infeasible and therefore you cannot do much about it. In the final tableau from phase 1, the last row is replaced by the actual cost function equation. The basic variables, however, should not appear in this cost function, and pivot steps must be performed on the cost function equation to remove the basic variables from it. We treat the cost function as one of the equations in the phase 1 tableau, and any removals are performed on this equation in sync with the remaining equations, and the cost function then will be in the correct form to continue with phase 2. So again, this seems a bit complex, but if you look at any solved example, for example, in my book or in some other books, you will find that this is not very difficult to do, and it's something which you can get the hang of by doing a problem or two. So we are going to finish the linear programming part of this course here, and I'm going to mention a few more things about linear programming before closing this aspect. Now, linear programming is a very crucial subject in the field of OR. And direct application of linear programming as far as most engineering problems are concerned is somewhat limited, except I would probably say in the chemical engineering field where there are many linear programming problems. But certainly in mechanical engineering and such fields, most problems are nonlinear because the functions which govern the design process are typically nonlinear, as well as the constraints. Now, there are some important theoretical aspects of duality which we have not discussed in this course, and you can find them in dedicated linear programming books because this is an important theoretical concept in optimization. There are more efficient methods than simplex method which do not follow the boundaries of the feasible region approach which we have followed here, but instead move through the interior of the feasible region, and one such method was proposed by Karmakar. And again, there are papers and books on linear programming which will give you more detail about such method if you want to do research on that topic. Now, there is another type of problem known as conic programming, which is a generalized linear program where you add a nonlinear constraint to the problem which requires the design variables x to be in a convex cone C. So in such cases, all the nonlinearity is put into the mathematical structure called the cone, which can be quadratic, for example, and therefore there are problems where you can consider conic programming, which could be thought of a generalization of linear programming and is important in some aspects of mathematical optimization. So again, I will end this lecture here, and hopefully you have got a good background in terms of linear programming and you are capable of solving problems using the method of getting all the basic feasible solutions or using the simplex method. And I encourage you to look into the book or on some other books on this topic and solve some examples to get a good feel about this method. And then we are going to proceed to the next phase of constraint optimization, which is the penalty methods. And in these penalty methods as well as barrier methods, we are going to somehow add a penalty to the objective function where violation of any constraint is penalized. So that is something which is done in the penalty method. And as far as the barrier methods are concerned, you can think of this like a moat or a wall which is placed around the feasible region, and essentially you stay inside this particular region to solve the problem. So again, these methods have become important because the prevalence of stochastic optimization means that you can often use these kind of penalty functions to solve problems using genetic algorithm or particle swarm optimization or Firefly algorithm or any of these new methods. And these methods are not very sensitive to non-linearity which can take place at the boundaries of the feasible region, and therefore these methods work well with the penalty type of method. So again, that is why there has been a renaissance in the penalty type of methods in recent years. And of course, there are many methods which are there for solving constraint optimization problem using the classical gradient based way of thinking. And so we are going to discuss a sample of such methods also. So I will see you in my next video, which will be lecture 33.